do try to give you guys the points where you earn them, but if I'm grading by rubric, I can't stray from the rubric, right? And so on your midterm exam, same thing occurs. If you say it but you don't say it, I can't give you your points. And I really want to, but I'm trying to hold myself accountable for your sake as well. So let's go ahead and talk about number 1 and 2, okay? So I'm going to pull it up through my PDF here and explain as we go. So this is an old one. I have my a little bit newer one, which I'm a little bit more concise now. It used to be like really that paragraph wordy. So I'm sure some of you guys are long-winded as well. But number 1, what do you guys say for the favorability of the products? Yay or nay? No. No, so not favored. So when you answer the question, you have to say no. The products are not favored. The reactants are favored. And that's because the reactants are favored because they have lower potential energy than the products do. So if you state lower potential energy, you're in good shape. That is your 1 point with explanation. Thumbs up? Can I move on? 1 point with explanation. Reactant. So no, the products are not favored. Reactants are favored because they have lower potential energy than the products. And if you saw that from your, I drew a reaction coordinate to support it as well. You don't have to. You can just note that the delta H is endothermic, and so that should give you indication of that as well. Part 2 talks about entropy. So it's asking, is the forward direction favored? So yes, the maximum entropy is attained in the forward direction, meaning formation of products, because there are 2 moles of gaseous products compared to only 1 mole of gaseous reactants. So the disorder will increase in the forward direction. So you must state something about the disorder increasing, and that yes, maximum entropy is attained by going in the forward direction or formation of products. 1 point with some sort of explanation related to that. And if you're looking at your paper, and you might even see this when I'm grading you, like for your kinetics test, I tried to underline where you explicitly state something that gets you a point. So when you're underlining something, that might say, hey, I said it here, this is where I got my point or my 2 points or so forth. Part C asked about not right. Part C says state whether an increase in temperature drives the reaction to the right, left, or has no effect. Explain. So increasing the temperature drives the reaction to the right due to Le Chatelier's principle. And this is the phrasing that I think is really very concise that might help you along with this. Endothermic direction, or the endothermic direction, is favored to consume the additional energy to reestablish equilibrium. I'll say that again. The endothermic direction is favored in order to consume additional energy to reestablish equilibrium. It's all about reestablishing equilibrium, because if it's at equilibrium and you stress it with a stressor, for example, temperature in this case, Le Chatelier's principle states that you must counter that stress or remove that stress. So when you shift in a direction, that's the case. You're countering it or you're removing it. So that's 1 point with mentioning shift right with an explanation to support that. Thumbs up, can I move on? Thank you. And then lastly, question says, a decrease in volume drives the reaction to right, left, or has no effect. What did you guys say? Shifts which way? Left. Okay, so you must connect the dots here though. So increasing the pressure, decreasing the volume causes an increase in pressure. The stress is too much pressure. If the stress is too much pressure, and a lot of you guys got this wrong on your equilibrium free response. If the stress is too much pressure, I must shift to the side with less moles, because less moles causes, but why does it cause less pressure? Collisions with what? It has to be the container wall. Collisions with each other, molecule to molecule, doesn't necessarily cause a ton of increased pressure, because you can't feel that pressure. It's the container walls that's being inflated or held up by these molecules' pressure. Yeah. Maybe not on this one, but some of the other ones that specifically relate to, well, no, maybe on this one. I'd have to go back and look at this FRQ rubric more in depth to see if it says collisions with the container wall. But if you say increased moles, if you say more moles on one side versus the other, they usually do give you credit. But this is from 1981, and they've evolved since then, so I'd have to go back and check. And we're in this will be our 2017 exam. They probably have evolved a little bit to be more specific in their explanations. And I applied to be a grader, and I'll know in January. I'll know at the end of this month if I'm a grader for this year's exam. But my friend is, and she gives me some insight on how in-depth it is, so that's what I'm trying to make sure we're clear with our words here. Like, for example, the intermolecular forces debate, if you say bonds broken at all in intermolecular forces, you've already like not gotten any credit because bonds are not broken. It's the attractions. It's between molecules that are broken. So if you say the word bond, they don't give you credit. Little things like that. She's giving me some insight on. Okay, so I think we're good with this one. This was really a 4-point question. So on your midterm and on your AP exam in the spring, in May, you have 3 long questions, and they're like A through F or A through G. They're long, and they take 20 to 23 minutes each. They're worth 10 points. And then you have 4 short questions, which are usually A, B, A, B, C, A through D. They're fairly short, but they're a lot of times very specific explanation-based questions, something like this, or one calculation with explanation on how does that calculation occur. So they're fairly short, and they're only worth 4 points each. So the long questions, which are an hour of your time, that's worth 30 points. The 4 short questions are only worth 16 points. So it's worth it to get those short questions done really fast if you want to go back and jump on the longs. But if you get stuck on a long, just move past it because you need to go ahead and get those easy short questions. Okay. So second question, and this is a good one. Wink, wink, star this, please. This is the partial pressure one that a lot of you guys had some troubles with on your equilibrium exam. And it takes a moment to kind of go, okay, I know partial pressure is important in total pressure and in KP, but KP and PT are not the same thing. So in this case, the question asks, what's the total pressure? What's the pressure if none of the SO2, Cl2 had been dissociated? That basically means just like, what's the pressure of this guy? Well, this guy has 3.5 grams. You convert it to moles. You got 1 point for getting your moles, and it could have been inherent. So like I should, on my paper I did last night, this step I did in my PV because an RT. So it's called an inherent point because you did it. You didn't show the appropriate moles. But once you take your PV and RT, use your ideal gas law, constant temperature and volume, you should get 0.800 atmospheres. If you didn't get 0.800 and you just put 0.8, you may not get that point. They only have 1 true question that they'll grade for 6 weeks on the final exam, but we don't know which one it is, so we do correct 6 things on all of them. Okay, so that is a 2-point question there. Okay, who got that? Okay, how did you guys set up the next step, the next part? Alvin, how'd you set it up?
1.43 equals 0.8 minus x.
Okay, so he set up an ice box to get the equilibrium partial pressures, and that's x, and ignore my scratch artwork here. That's the 0.08 atmospheres that you got initially minus x, and then x and x. Those together, summed together, equal P total. And that's what he said was 1.43 atmospheres, which they told you is equal to x plus this combination, but then you simplify and create 1.43 minus 0.8, that gives you x. X is 2 of the answers, right? So each of the partial pressures of those 2 products, which were sulfur dioxide and chlorine gas, you got 1 point for getting x and setting equal to those 2 partial pressures. Your second point came from the actual subtraction by doing 0.8 minus x, which you got as 0.63 atmospheres here to get 0.17 atmospheres for your original reactant. So that's a 2-point question. It could be occasionally a 3-point question. This one, I don't know if they gave you points for your setup of your ice box, because you don't absolutely have to set up an ice box. You should just recognize that there's production and consumption, but units and all should be included here as well. So in KP, a lot of times you might see a unit of atmospheres in the actual KP itself, which is going to be this next part, but they don't take off points unless if they don't take off points for not including KP units, because for Ks we generally never ever include units. It's unitless. So this part C, you got 2 points. You had to set up the KP constant. So the KP expression, or a version of it with your values plugged in, gave you 1 point. So setting up the expression, what's different between KP and KC in our expression setup? Say again. So we say partial pressure by putting P and then the little subscripts. We also use parentheses, not brackets. Okay. For KCs, you must use brackets, and then you're good for there. So that's 2.3 atmospheres, or 2.3. Lastly, the question says something about temperature. Identify, or if the temperature were raised to 500 Kelvin, what effect does this have on the equilibrium constant? It causes a shift which way? Y to the right. Because it's endothermic, and what do we say when we increase the temperature? What's the phrase? Favors the endothermic direction, which is the forward direction in this case. So it happens to make more products. So it produces products at a faster rate than it consumes those produces reactants in the reverse direction. As a reminder, equilibrium, what is the true definition? Oh, sorry, let me recap this. Increase in the product concentration or the number of products would then cause the K to increase. So this is a 1-point question with the correct statement of the K value increasing due to the shift right of and the products being produced at a higher rate. So that combination gives you 1 point. But as a reminder, how is equilibrium defined? Okay, so rate of forward equals rate of reverse. Okay, how are rates written? Rate laws. Concentration of reactants, thank you. Amount of products, free number of products, and rates, right? Now we've got equilibrium under our belt. That's when it starts to intermingle with kinetics a little bit too much, and we need to really kind of reestablish that. So it's like KF, K, the little k, rate law constant K, of reactants, whatever they are in brackets, raised to some power, right, equals KR, which is the reverse rate law constant, times their reactants, which are the products, but we still call them reactants because they're reactants of the reverse to their power. So you technically could say at equilibrium rate is equal to rate, therefore rate law is equal to rate law. I could even have you solve for something in here given all the other variables. Yes? It's basic algebra, but you have to be given those variables. For a first order reaction, what are the units of K, of the rate law constant K? First order. Just per second. So 0 order is molarity per second because that would then equal the rate itself, which is molarity per second. For first order, K is per second or per time, whatever it is. Let's say this number here is third order. What would the K value have to be? K units have to be? Per, yeah, so that would be 1 over molarity squared times time, or seconds in this case, because that would need to cancel out 2 the molarities and leave 1 molarity on top. So thinking about those units is still important for us. Okay, let me stop there for a moment. I have a couple of things I like to do. Recap one more time a little bit more about the reasoning behind strong acids and strong bases, because that's going to be used in, I think, like number 4 on here. That way you're not struggling. And then we're going to jump into Le Chat's a little bit more. So I'm just going to have you guys read this and just make sure you're comfortable with this. Do a quick read of this. This is stuff from yesterday. I need to finish up with you. Just make sure that's clear in your mind. And as a review from Honors Chem a little bit, how does atomic radius trend? Nice. Atomic radius is how I taught it in Honors Chem. Hold up your hands like this. Right hand radius. Turn your right hand over. This is the way atomic radius increases. It increases to the left and down. Specifically, we're looking at the trend mainly down the group here in the halogen group. And that's atomic radius. Everything else, including electronegativity, ionization energy, and electron affinity, are increased in the opposite direction. So basically you make like a little picture with your hands and snapshot of your film, okay? So really electronegativity is what we're looking at here. But that's your strength differences and a little bit more of the comparison there. And then this is a paragraph of that. That first part there is very similar. But this down here talks about those those oxyacids with the oxygens embedded within them. And so one more time, the more oxygens, the more significant the electronegativity differences are. So if you have one area that's very electron dense, we say it's got a high electron density, and one area of the molecule that doesn't have a lot of electrons, it's got a low electron density, that creates a very, very, very polar molecule. And so that bond that holds it together is likely to break because often you'll have, and this is the example of hypochlorous, chlorous, I'm missing one, chloric, oh, and perchloric. That's the difference between these and why one's a strong acid and the other, or one's a strong acid, the rest of them are not, because the bond between here, is that strong or weak? Strong, because there's not a lot of electron density on the left-hand side of the molecule. Whereas down here, this is very weak, and so what happens is this is just 2 electrons, right? There's just 2 little electrons being shared in that bond. They are like, hey, I'll just go along over here and join the rest of the electrons, and it basically donates its electrons to the chlorate ion, which is why it gets a negative charge, and the H plus pops off. It's very easily going to do that when you have a significant difference in your electron density. Okay, so that's just some more multiple choice based things because that's where some of that's just memorization of facts and understanding as well. Okay, I'm going to skip this for a moment. Let's go do a little bit of common ion effect as it relates to Le Chatelier's and acid bases, and we're going to talk about where this is in your packet shortly, but let's just talk about this at first. We have acetic acid, we have 0.1 molar. How would you solve for the pH? Shout it out when you're ready. Say again? Icebox, because it's a weak acid. You have to categorize it in your mind first before you jump to conclusions, okay? This is a weak acid. Ka value is 1.8 times 10 to the negative fifth. You do an icebox. You solve for x. X is equal to the H plus concentration of that ice. And that value, I already done it for you guys just because I knew that you could knock this out if you really wanted to. When you do the pH, it's 2.87. Okay? So that's an acidic solution. That's good. It's a weak acid, okay, and it's 0.1 molar, which is not horribly significant, but it's not too dilute. So that's why the pH is closer to 1. Okay, so here's our acid dissociation, also known as ionization. And as we go down here, I want you to tell me if I add sodium acetate to this, what would that do to the equilibrium? This is my equilibrium, right? So I have this acid, it's dissociating within water, it's forming acetate and hydronium. If I add sodium acetate, what would that do to equilibrium? Tell me what we have added that's significant to our equilibrium. Okay, so Levi, go for it.
It would shift to the left because once it's gonna ionize because it has sodium, and then once that happens, you're gonna have a bunch of acetate in your solution. It's gonna shift back left.
Correct. So you're saying that you add acetate. Well, acetate happens to be a product, right? So adding a product would mean we have to shift left to reduce that stress of too much product. Because what happens is if I add a product, what does that do to K? Okay, well, sorry, what does that do to Q? Let me go back, because it's not truly K, it's not at equilibrium. What does that do to Q? Q is the same exact setup as K, okay? So it makes Q greater than K is what you're saying? Okay, so if you add a product, you have too much stuff in the numerator, Q is greater than K. You need to get Q equal to K once again. That's another way to explain it via Le Chatelier's. And so that's going to cause a shift left to do that. All right, so as that shift to the left occurs, what's going to happen to the hydronium concentration? So you say it decreases. Okay, so what's going to happen to the pH? It's going to what? It's going to increase. Okay, so you see how we're now connecting Le Chat's to acid-base equilibrium, which would then affect our pH. Okay, so this is going to lead us into buffers soon, but this is another version of the common ion effect. There's multiple ways to state this though. Common ion meaning simply straight up a common ion, meaning acetate was added to the equilibrium. Secondly, I could have, let's say I add a base to this. What if I add sodium hydroxide? Is there truly a common ion? No, but the common ion effect still occurs. The common ion effect is adding something that can intermingle or interact with the equilibrium at hand and cause a shift. What can this base do? What can it react with? It can. That's the only thing. Like, it's not going to react really with that. It's going to revert. Not really with water. Acetate, no. If it forms sodium acetate, it would just reionize. Nothing would happen. But what it could do is it could have an OH attract to the hydronium, and what does that make? 2 waters, right? Pure liquid water, which is not going to dissociate. and it's not going to be included in equilibrium. So basically, what have we done to the hydronium concentration as the OH reacts? We take it out, right? So we decrease the hydronium concentration simply by adding a base. What shift would occur once that happens? We would shift right in order to get the hydronium concentration back up, but it's never going to go back up 100% to what it was before. So what's going to happen to the pH? It's going to increase. One, duh, we're adding a base. It better increase. Second, the hydronium's not going to go up as high as it once was, so it's still going to increase. So they both agree. Does that make sense? Some of you guys are like sleepy, but yes, it does make sense. Okay. All right, so let's talk about this a little bit more. I think we're. Oh no, let's go ahead and do this one because this is prefacing us for our problem set. I want you to find the pH of this solution, this mixture of solution. Think about what you have to do. Do you guys need help setting up, or can someone maybe tell me how you're setting up? Not a soul? Anybody tell me how they're setting up? Okay, so icebox, find X, but in your icebox, what is already present? Concentration of acetic acid and acetate, not sodium acetate. Sodium acetate itself is not in our equilibrium. We're doing an acid dissociation still, so HC2H3O2 mix this stuff. So you already have this as 0.1 molar, and you already have acetate at 0.050 molar because sodium acetate dissociates into 2. Okay, so that's your I in ice. And yes, we do find X, so we're subtracting X. Nobody cares about water. Add X, add X. Sorry, my phone is possessed. What is the Ka of acetic acid? I'm going 1.8. Sometimes they'll be different on your, from the back of your book to your tables. I'm sorry, guys. Okay, so 0.050 plus X times X over 0.10 minus X. What are you likely going to do? Neglect, and then we will double check to make sure that's fine. Don't just willy-nilly neglect. On last year's AP exam, they had a reaction that was, the ice box was complex. It was like quadratic. So everybody's like, yeah, we should neglect. And as you did it, you realized that you couldn't neglect, and so people freaked out. And I even did it too, and I was like, oh no, this can't happen. And then everyone realized that it was a completion reaction. It wasn't even an ice box. So do double check that your X is able to be neglected. So that makes our math much easier. 0.05 times X over 0.1. Manipulate. So what's X, guys? Negative fifth. Yeah. 3.6 times 10 to the negative fifth. Can I get a thumbs up if anybody else got that? Awesome, thank you. Okay, so that's molarity, right? That X represents what? That's significant for us. That's hydronium, right? So then, if we have hydronium, we can find pH very easily. Can we do a quick double check on can we neglect this? What would you be doing? That divided by 0.05. The smallest thing you would have added or subtracted to, or from, based on the numbers given to you. So when you do that divided by 0.05, what do you get? Something to negative 4 times 100. Did you multiply by 100? Still, it's less than 5%, so we're good here. All right, so that's our hydronium. So then we can find pH. What's pH? Negative log of X. Anybody? Thank you. 4.44. We're still in acid realm. That makes sense. But what I just proved to you is what we just did theoretically as a qualitative reference. We did as a quantitative reference now, and they both agreed, right? So basically what we did back on that first slide was we said, what happens if I add sodium acetate? And you guys said, oh, it's in a product. We're shifting to the left. The hydronium concentration decreases. The pH increases. So this was the pH before any acetate or sodium acetate was added, 2.87. We went ahead and put that logic into an icebox with some values given, found our pH to be 4.44, so both of those qualitative and quantitative reasonings agree. You can expect something like that on your exam, on your midterm, where either you explain it theoretically or you do it mathematically. Okay? And so that's referencing the common ion effect, but in this case, it's basically, we already have some of the ion in the solution, so the acid is not likely to dissociate quite as much because there's a barrier to dissociation because of that presence of the common ion. All right, so I think you're going to be fine with this, but let's just do one more check here. Tell me what would happen here. What did if I have sodium acetate as my actual original reactant, and you can see I've taken the NIE of that, taken the sodium out of the picture. Sodium acetate, so acetate plus water makes acetic acid and hydroxide. What happens if I add acetic acid? So you're saying I've added a reactant or product. I've added a product, so it shifts left. What happens to hydroxide? It goes down because you must consume products to reform reactants. And so if hydroxide goes down, because there's always an interplay in a solution with hydroxide and hydronium, and you know that together they complete each other, right? So hydronium concentration times hydroxide concentration will equal the Kw constant 1 times 10 to the negative 14. So if I decrease hydroxide, what has to happen to hydronium? It will slightly go up, so what happens to pH? It decreases, right? So either you saw hydroxide going down, so you know, hey, it's less basic, it must be more acidic. And when I said increasing hydronium, you have to note that increasing hydronium means more acidic, so pH goes down. So you can definitely, I think, see the picture there. All right, look in your packet. And you guys, I'll pull it up here too. I'm going to have you guys just do one of these. I don't think you need to do both of these examples. So start with number 1. Right now it's A through, I want you to start only with A through C. I'll show you where it is in your packet, maybe from Chloe's, so I can see it here. So it's on the picture, it's on the page with all those charts like this. The charts, and it's right under the first chart. It's a common ion effect, A, and it starts you off with potassium hypochlorite. Sorry about like number 13 package. We still have an hour in class. You guys are awesome. Take. Is it longer? Well, because we don't watch them. Oh, shush. You're listening out loud. I need to pull her up on YouTube. You're not a great person. So just start with A through C for now, and then once you get through that, you guys let me know how we're doing, and we'll move on. Yeah, look into the room soon.